Hello, I'm Josh Stoddard, an engineer at Tanium. I'm here to present Reveal, our implementation of a federated search engine operating on unstructured file data at rest on large enterprise network environments. When we look at search in enterprise network environments, we're typically talking about thousands to hundreds of thousands of individual endpoint machines. Each machine contains hundreds of thousands of searchable files. That means that we're often working at scales of billions of individual files to search. The task is to make this corpus of data queryable on demand in human time. For comparison, Google estimates that the number of unique pages in the indexable internet is in the single-digit billions. So we're operating at a similar scale. Other search engines at this scale, like Google and Bing, use what's called a centralized architecture, the main tenet of which is that search data and query operations take place in a central location using dedicated resources, such as a Google data center. An advantage of this approach is very efficient querying. This is what allows Google, for example, to service tens of thousands of queries per second with latencies of under a tenth of a second. Conversely, all of this data needs to be ingested and centralized, and this can come at a cost. There are some challenges related to ingestion and indexing of data in centralized environments that Reveal is designed to address. For one thing, sensitive data is not always transmissible to a central location. Sensitive data, if it is transmitted, can risk exposure. And there's certain legal frameworks in which certain types of sensitive data are legally not allowed to cross certain geopolitical boundaries. There are technical challenges as well around the ingestion of data, such as limited network bandwidth or requiring that the data be fresh, limited age that the data can be. Reveal addresses these scenarios using a federated architecture in which every endpoint machine maintains its own local searchable index corresponding to the data that's present on that machine. In this way, each machine can operate autonomously and independently to index its local data to its local searchable index. This translates to index to data age limited in hours rather than days. Conversely, aggregation needs to happen at query time under this architecture. For a query to produce full results, it needs to be evaluated against each of the individual endpoint indexes. In order to make this practical, Reveal offers a three-tiered search approach. This is a recording of a laboratory environment with 1,106 connected endpoints. I'm going to create a search to look for VLDB citations within that corpus of data. My search is going out to all of the endpoint machines, and they're responding. In the left, we see a percentage. This is the percentage of those 1,106 endpoints that have responded so far. The rows in the table correspond to the individual machines that have found results for this phrase that I'm searching for. Now I'm going to click on one of these machines to connect to it directly and explore the data local to that machine in more detail. As we can see, there are 3 files that it found that contain the phrase I'm looking for. I'm looking at the first one, and now I can see the match that it found in context. This data is being read directly from disk in real time. And as you can see, we found some citations that I was looking for. Now going back to the results, it's been about a minute, and nearly every machine in the environment has responded. Now I'm going to create a more specific phrase to narrow down the results that I'm getting. The machine that I connected to before is still available, so I can dive right in and see how my updated query affects the results on that machine, or I can wait for the global results and explore other machines. I'm going to click on another machine to view the results on that machine. These queries are on demand in that I'm creating an ad hoc phrase that I'm searching for in as fast as it's able to let me. Reveal also supports proactive search using saved searches and pattern criteria that can be used to alert on when new matches are found or to classify files. Critical to Reveal's ability to do this is its ability to communicate with every machine in an environment within a few seconds. It does this by virtue of the Tanium Communication platform. This is a communication architecture built around the idea of linear orbits. A linear orbit is a self-organized chain of peer machines optimized for peer-to-peer connectivity efficiency. In practice, what this means is machines that are connected to via a local area network are able to use those local connections for very efficient peer-to-peer communication. Each machine in the linear chain inserts its results to a query with the results from the machines coming before it, using compression and deduplication to control the size of the full payload. Only the machines at the beginning and at the end of the linear orbit need to communicate directly to the remote server. In this way, Tanium is able to optimize for its use of wide network connections, and this allows it to scale to the hundreds of thousands of endpoints while still getting full results from available endpoints within 60 seconds. In order to operate as a federated architecture, Reveal needs to operate locally on the machines where the data is stored. This means it needs to operate on machines like workstations and file servers, whose primary purpose is not to service Reveal. Reveal needs to run as a background process without adversely impacting these primary functionalities. To do so, Reveal imposes limits on its use of shared local resources in terms of compute, memory, file I/O, and storage. These are configurable and allow Reveal to operate on any endpoint that it needs to operate without adversely impacting the primary business functionality of the endpoint. One of the main use cases of Reveal is indexing and availability of sensitive content across an environment. As such, all of the searchable data and the contents of a query made by a Reveal operator are considered sensitive and protected. Reveal does this using an opaque tokenization scheme. When it indexes data for search, it includes a one-way cryptographic hash in its token generation scheme. This produces tokens that are comparable for equality, but are opaque in terms of their semantic meaning. The same tokenization is applied to queries when they are generated, and the query payloads that are sent across the network and all of the processing that takes place for queries is done in encrypted token space. In this way, none of the data that is transmitted or persisted is reversible. As we saw in the demo earlier, part of the Reveal workflow includes a direct end-to-end connection to endpoint machines to view its data as it lies. These connections are end-to-end encrypted between the endpoint machine where the data resides and the machine of the Reveal operator with sufficient privileges. The unencrypted data that we saw in the context of the matches is sent over this connection after being read directly from disk on demand on the endpoint machine, and it is not persisted in either place. In this way, that data goes only to the privileged user that requested it and is not persisted. Finally, every time Reveal is installed, it creates a unique fingerprint for that installation that is used in the creation of tokens. That means tokens generated in an environment are only compatible with other tokens from the same environment. If a Reveal query is intercepted, it can't be reverse engineered by transplantation into another Reveal environment. Thank you very much. More details on Reveal can be found in our white paper, and thank you for your time.